Okay, last one. Now my arrow keys, not working. Okay, so it seems like we should have talked about the ionospheric layers in the beginning, but we'll do them now. And the critical angle, scattering, invis, uh, propagation prediction, the radio horizon, which is the point-to-point VHF, UHF, and some space weather phenomena. So the ionosphere is that region 50 to 400 miles, which gets ionized by solar radiation and refracts radio waves. You can call it reflection. Effect is basically the same.
One of your previous drawings showed the signal going up and then following the layer and then coming down.
Right.
So if you thought of reflection, we could find a point where
Right.
it reflects, yeah.
Right. And
But
you could say it's reflecting off of this point or it's refracting down here.
Yeah.
The effect would be the same. So it's broken up basically into three layers, the D, E, and F layer, which we talked about. During the daytime, the F layer divides into two, where F2 kind of increases in height above F1. And then you have the D layer, which is energized in the daytime because enough radiation makes it through the F layer and the E layer to actually ionize the D layer. But the D layer doesn't do anything good. It absorbs signals. So that's a case where the solar radiation doesn't help us because it goes away at night. Therefore, you can use those low frequencies, which would have been absorbed. So with the F layer, or the F2 layer during the daytime, you can get up to around 2,500 mile hops. This chart shows the different layers and what happens to them over there in the shadow of the Earth, which is nighttime. And they show these bands on this one as the same width. I actually think they should be maximum width over here when the sun is perpendicular, and they should taper down to essentially nothing, I would think. But I didn't draw it. The main thing there is it's showing the difference in the daytime versus the nighttime layers.
Wonder if it's actually asymmetrical so that it would be tapering up as it has been exposed more to the sun.
I would think.
And into the shadow, it would take off as it deionizes.
Yeah. And I would also suspect that the F1 and F2 start collapsing long before you get over to the dark. But that's just my guess.
So what determines if you refract off the D layer or the F layer?
Well, you're not going to refract off the D layer.
D, I mean the
E layer.
E layer.
Frequency, basically.
Your radio.
Nice. I knew there was a reason for this.
It's hexadecimal.
Yeah, hexadecimal.
What button is that?
DEF button.
Is that in the menu?
Yeah.
It's only on the higher end radios.
Well, I have one of those, but I don't remember that button. I have to look, but I don't understand the whole menu yet.
Yeah.
I've only had it for a year.
There's only 34 videos on how to work that radio.
Is that all?
7300, how about?
7610, I think.
That's a problem more.
Do you have a 7610 or a 7300?
7300.
Both.
Well, which one are you talking about?
The 7610.
That's I thought.
I see it more.
Yeah.
I don't use the 7300 much. I'm still learning how to use the 7610. Every time I look in the book, I can find something different. Although I've still never figured out, they show this picture because it's a dual receiver, and you get, two of the analog S meters and then two different spectrums. I have yet to figure out how to make that work. I can get the two S meters, but just a single spectrum. Every time I try to get two, then the S meters go back to digital. But they show it on the front of the book about it, so there must be a way to do it. But anyway,
That's a video number 30.
the F2 region is basically responsible for all the long hops. It's the highest ionosphere region up to around 400 miles or so. And it does condense into a single layer at night. So why is skip propagation via the F2 region longer than that via the other ionospheric regions?
Chuck.
And there's a nice little chart showing what happens with frequencies. Where the higher frequency, you're going to go straight through the layers. If you had one kind of in between there and that highest one that's refracting, it's going to just get refracted, but not enough to make it back. It is definitely proportional. Oh. Steve. What's the approximate maximum distance along the Earth's surface normally covered in one hop using F2? The middle layer, or the E layer, okay, is where we get the sporadic stuff and auroral. So you can go up to about 1,200 miles. So that's the main thing to remember. It's the F layer is twice the E layer as far as hop distance. So what's the approximate maximum distance along the Earth's surface normally covered in one hop using the E region? Because they have them both in there. You have to remember which one. And in 4 or 5 weeks from now, will you remember that? The D layer is the bottom or lowest layer. It's like 40, 50 miles up. And everything below 10 megahertz basically is completely absorbed during the daytime. That's why 20 meters works in the daytime. It's above 10 megahertz.
And the D layer is created from the sun.
Right.
The iron section.
Because the ultraviolet X-rays make it all the way down to the D layer. Well, actually, the ultraviolet makes it all the way to the surface because that's how you get sunburn. But more of it comes down than it does at night. You know, you don't get much.
Higher frequency ultraviolet does not make it through as well. The lower frequency ultraviolet does make it through, that's what burns us.
Okay.
If the other one made it through, storage. Yeah.
It hurts anyway.
Yeah, I understand that filters it out, right? That dangerous things, I think it's atmosphere that filters that out. Yeah,
Yeah.
I mean, it could be yeah, something like that. Not straight.
It does make it through window glass too,
Yeah.
And the higher you go, the.
because that's what fades your furniture and your
Yeah,
carpet.
B and C. does that.
So which ionospheric layer is closest to the surface of the Earth?
AD.
You know, it's one of those, I always wonder what happened to A, B, and C.
About cross. That's restricted.
It was probably
Passports.
It's what?
Talking about the FAA airspace. FAA regulated that out.
Okay.
AD.
FCC doesn't have jurisdiction, so we don't care about it. Which ionospheric region is the most absorbent of signals below 10 megahertz during daylight? Why is long distance communication on the 40 meter, 60 meter, 80 meter, and 160 meter bands more difficult during the day?
Just
Charlie.
Okay, critical angle. It's the highest takeoff angle that will still be refracted. So you can see on this chart, you've got a couple takeoff angles that, well, I should say refracted back to Earth, because they're all being refracted, but they don't make it back. And at a certain frequency, when you get up into the VHF, UHF, they're just going to go straight through. There's really no refraction at all.
The same thing when you're underwater and you look up.
Yeah.
You can see out in the cone, but once you hit that critical internal angle of reflection, you come back.
Right. Looks like a mirror. And this is kind of showing the skip distance, which obviously increases with the angle, the takeoff angle. So you want the lowest takeoff angle that you can get for the maximum hop. I'm not exactly sure why you would care about getting close to the critical angle unless for some reason you specifically wanted to try to get a station that was that distance away. Because if you're going for the low takeoff angle there, it's in the middle of the skip zone, so you're not going to make contact at the low angle. It's basically a dead zone under the.
I don't know how you would do it, but if you were on the East Coast and you wanted to do a single hop to get to the West Coast, then you would want the low takeoff angle.
Right.
But how would you know?
You'd have to adjust the height of your antenna.
Yeah.
That affects the takeoff.
I've seen guys with.
Or switch to a vertical.
On their towers that they could actually change the height. I'm like, well, you guys really get into this crap, don't you?
Wow. Yeah, switch between vertical and horizontal, you're going to get a lower takeoff angle on the vertical.
Yeah.
What does the term critical angle mean as used in radio wave propagation? And it says under specific ionospheric conditions, One of those would be when the luff is lower than the muff, right? Because it's not going to work if the luff's greater than the muff.
Oh,
Yeah. Oh,
well, wait a minute.
What?
because it's going from the horizon
Someone
up.
said C.
You're right.
It's, yeah, you guys said C, but it's the low.
It's the
it's the
low.
highest. A little,
Yeah.
if you turn it horizontally, that's fine, but as you go higher and higher, eventually you're gonna hit the point where it just goes through instead of
Right.
refracting. It's with respect to the horizon, not with respect to vertical.
Did you read all four or did you stop at Charlie?
I'm not gonna answer that.
Oh, that's it. You know, everybody does it.
So, question then, going back to earlier. The refraction coming off the ionosphere makes it ellipsoidal.
Right.
And that's why, for example, in direct wave communication, VHF, UHF, polarity matters. If I'm transmitting vertical and somebody's on horizontal, I'm taking an attenuate.
Right. You hold your walkie-talkie this way and your signal is, yeah.
I'm mismatched in polarization, but we
Right.
don't see that. That's why somebody working vertical HF can still talk to somebody on horizontal because
Right.
depending on that refraction.
Because you're always, because it's rotating, you're always going to get part of the signal regardless of your orientation.
Yeah. Wouldn't it be fun if we could make a size effective circular polarized antenna
Yeah,
for HF?
you'd get better signal.
Yes, you would. If it's right hand versus left. You might have to get both depending which direction. you go.
Yeah.
Who knows? I don't know.
Yeah. And it didn't say whether when you had ordinary and extraordinary, whether one was left, one was right or not.
Vertical, yeah, vertical collateral time.
Okay, critical frequency. For any given incident angle or takeoff angle, there's a critical frequency where it refracts. So once again, if the frequency is higher than the critical frequency, it's going to pass through or not be refracted enough to make it back. If it's less than that critical frequency, then it can be refracted back to the earth. So it,
Explain why the 20 megahertz signal passes through and refracts.
as opposed to the 21.
Two
No,
slightly
you've
different
got two
angles.
20s.
Oh,
Two slightly different angles.
They're different angles.
I hadn't noticed that, but you're right. It,
It's showing that the higher you go, that you have to.
Right.
The incidence critical angle.
right.
Applied to frequencies,
This chart's showing both.
yes,
Yeah.
it's a little confusing, but if you separate it out.
See, it says frequency versus critical angle. Okay. So we have over there on the left, we have a higher incident angle at 20 megahertz. Okay.
Take off and keep going.
And it's too high, so it passes through.
Oh.
At 20 megahertz at a lower angle, it refracts.
But 21 is still too high, and so it keeps going through.
Yeah, I think that's what's showing. Wow.
If you remove that top 20 megahertz line. And then you deal with the critical frequency showing that at this takeoff angle for the lower line only going out from the tower. 21 megahertz is not hitting critical angle, so it's going to go through. 20 will.
Yeah, but the other
That-
20 is showing what happens if you exceed the critical angle.
Yep.
That's showing two
Two different effects.
critical angles.
Well, critical angle and
No, that's showing two takeoff angles.
Yes,
right.
Yeah.
and showing frequency sensitivity to the takeoff angle. And showing that at a specific angle that you can now see the difference between critical frequencies.
I got it now.
Okay. Of course, I don't know why I care.
Confusing.
Was that for, did you hit that earlier module?
Other than it's, huh?
You just put that in there to make my brains.
Well, I didn't put it in.
Just checking to see if you're paying attention.
So what is meant by the term critical frequency at a given incident angle?
I didn't read it out there.
Scatter propagation. Okay. A portion of the signal actually gets reflected back. Or it's not refraction, it's actually reflection off of particles and things. What's why they call it backscatter. So you get a small portion of the signal that's coming back at you or sort of in your reverse direction. So it allows you to pick up signals or make contact with people that would normally be in the skip zone. So you're going up and you're refracting over here 2,500 miles away, right? But you get some backscatter on the way up. So you're getting your signal coming back down into places within that skip zone that normally you wouldn't have any signal at all. And obviously it's gonna be a weak signal and it's not consistent, reliable. And you can have kind of a multipath effect because of the different scattering. So you could have your signal coming different paths back to the same point. This top one is showing showing the scatter effect where you've got these pockets, they call them, of with different refractive indexes that's causing that scattering effect. They don't show any here. Well, I guess actually they do a couple. So you can actually have some of it coming back towards you as true backscatter, but it allows you to get to places within that skip zone. This other one is when we talked about tropospheric ducting, showing the effect of how it goes through the duct before it goes back to Earth. Kind of like having the same as the chordal stuff at night. Let's see, what was this one? Oh, there's just another one I found kind of showing some of the different effects where you get some short path and long path things going and turbulence in the atmosphere. You can get all kinds of weird effects. So what type of propagation allows signals to be heard in the transmitting station's skip zone?
Probably.
No Faraday?
Sounds cool.
Why are HF scatter signals in the skip zone usually weak?
Oh.
What's the characteristic of HF scatter? Fluttery. What makes HF scatter signals often sound distorted?
Yeah.
Alpha? Got a lot of alphas.
Well, it should have.
It's not getting scattered from the ionosphere, but it's troposphere, which is below the ionosphere.
He's right.
What's that?
It's not going up to the ionosphere.
The scatter signal from
Although, well, actually, E layer is part of the ionosphere, but it's not.
the scatter they were showing really here.
Right.
Right, they're showing that troposphere on a diagram to show.
It's really the multipath part of it.
On the drawing you had up there, the picture you had the one signal going up. And then a whole bunch of them coming down. Up that,
Not that one. That one,
See that?
scattering,
yeah.
yeah.
So you got the
So-
troposphere and then the stratosphere and the ionosphere.
But you can see there's a couple where you've got it being scattered two different paths back to essentially the same point. It's unpredictable.
Oh, I guess I see that, yeah. Yeah, they are. Okay.
Okay, in this near vertical incident skywave. So it's used for short distance propagation using high elevation angles where normally you lower the antenna very, within like a tenth of a wavelength from the surface of the earth. And it gives you a radiation pattern that's almost vertically, like a big vertical lobe, which lets you make refracted or skywave contacts within a couple hundred miles. And that's why the military, I don't know that they developed it, but they make use of it because you can be in areas where you've got mountains and all kinds of obstacles and you can't do line of sight to somebody that's 20, 30 miles away. But with NVIS, you can make contact with them.
If you've got your antenna close to the ground to take off at a vertical angle, but somebody else has got theirs up higher and their angle's lower, they may be able to hear you, but may not be able to talk back to you.
Talk back.
Right.
Because theirs is shooting over your head.
But that's why the military vehicles have the same antennas. We have a guy in one of the clubs up north that's gonna try NVIS on his, run a line a few feet above his seawall and see how it works. Yeah. That's kind of showing a typical NVIS setup, where you've got a dipole very close to the ground. And what the effects would be, and they're, I guess they're in Afghanistan or something, so you're hitting in all these valleys and things that you normally wouldn't be able to get to.
Same thing by running across the top of a vinyl fence.
Yep.
Vinyl.
What is near vertical incident skywave propagation? Okay, prediction techniques. There's a lot of networks out there. There's Reverse Beacon, there's PSK Reporter, where different stations update information. And you can see these as kind of real-time plots showing these point-to-point signals. There's also this thing called VOICAP, Voice of America. Is it Cellular Patrol? I don't think so. It's something propagation, I forgot. And it does modeling of HF propagation. So what type of data is reported by amateur radio propagation reporting networks? What does VoyaCap software model? Okay, some of them use the A index and the K index. And they're both indicators of geomagnetic activity. The higher the index, the more geomagnetic activity, which usually means it's negative propagation. Not necessarily negative, attenuated propagation.
So if it's lower, the A and K index.
The better.
Better.
Right.
Okay.
You would like the index being, let's see. K is 0 to 9, so you'd want that to be 0. And A was some other range, I forgot.
Why the polar paths point, why would that be more specific to? Or why would the polar path be more effective?
I think for the same reason as the no, I'm trying to remember what it was. That affects the high latitudes because of the stronger magnetic field. So the geomagnetic storm, which is what this is trying to measure, is probably going to have a bigger effect.
And the bands are thinner there because as the fields collapse, come back down to the poles, you have less protection there.
Yeah.
Okay.
And then there's the, oh, we didn't come up with it yet. The auroral oval, basically inside the aurora, because of the way the magnetic field is. You see this aurora as kind of a big circle or oval with a hole in the middle. What is indicated by a rising A or K index? I think it's critical frequency.
Oh, yeah.
Which of the following signal paths is most likely to experience high levels of absorption when the A or K is elevated?
Way of saying polar. That's obfuscated.
Huh?
That is a very obfuscated way of saying polar.
I didn't write the question. Okay, the B sub Z is another measure of the interplanetary magnetic field. That's the one that bothers me. I thought it was just the Earth's magnetic field. I didn't know that the other planets had much effect on ours. They're pretty far away. But
Sun.
Jupiter.
I think they were referring to the Earth's as part of the larger ecosystem of magnetic fields among planets and just therefore lumping it in.
I
Even
guess.
though it's just the Earth that affects.
Why didn't they just say inner instead of enter?
Why not just Earth's magnetic field?
Yeah.
Of
And they like to throw in those big words. One of the things it measures is the orientation, whether it's going north or south. So it's amplitude and direction. So when it's going south, that means that I guess because it means it's following the flux lines of the magnetic field of the Earth, but it's going to disrupt the conditions as opposed to more than when it's going north.
Is it different from the northern hemisphere to the southern hemisphere?
I don't know.
Because the flux lines of magnetic.
We pretty
would
much
be going
ignore
same
people in
direction.
the southern hemisphere, so I don't know. Yeah, it's a good question whether or not the B sub Z is just for the northern hemisphere or for the Earth.
Magnetic particles or field lines are still going in the same
Right.
direction, even coming back in the pole and south, but
Right.
it's.
I don't understand this at all.
What
I think magnetic field lines.
all it's measuring is the direction of the magnetic disturbance. In other words, you got a magnetic field that came from the sun, a storm, a geomagnetic storm because of that magnetic field. And it's disrupting communications and it's directional. So if it's going southward, in other words, north to south, it disrupts it more than if it was going south to north.
But it's coming in perpendicular. It's not going down through the Earth, it's going into the Earth.
Yes,
So.
but it's a magnetic field, so it varies and it has some polarization of which.
Well, yeah, think of it like a conductor, you know, and they got the fun. And
So I would assume if there's an E field associated with it, because as far as I know, you can't have one without the other.
have one water.
E field without an H field and vice versa. Because the magnetic field variation is going to create an E field. As it changes, it creates the electrostatic field. That's why they're orthogonal and back and forth. So if the E field part of it was parallel with the equator, then the magnetic field is going to be north and south, right?
Right.
So
So what's gonna make it?
I don't know,
Flip.
north versus south, I don't know.
It almost, southward orientation makes me start thinking of polarization, like polarized light, you know, but affected more in one direction than the other. It's the only thing I can come up with to sort of understand this.
All I know is that the BZ index tells you that it's north or south. And if it's south, it's bad. Badder than if it was north.
So I just Googled that. The interplanetary magnetic field. Says it's the sun's magnetic field as it extends out into the solar system carried by the solar wind. It acts as a link between the sun and the Earth's influencing phenomena like magnetic storms and aurora. Kind of got a picture like that when you had further.
Okay.
So that'd be the interplanetary part, but that's not.
The interplanetary meaning the sun.
And all the planets.
In the Earth apparently is the only two they mentioned there.
Okay.
Is it intra or inter?
It says inter.
Yeah, it says interplanetary.
Inter then is the first four planets.
Why the first
It's the new
four?
ones.
Because
Yeah, it is.
those are referred
I'm just
to
reading-
as
I'm
the
reading
inner
Google it,
planets of
right.
the solar
Is that off
system.
Wikipedia?
They're the rocket
just typed it in
planets.
Google, that's what.
Okay.
From Jupiter on out, they're
Gas.
referred to as gas.
I show very similar picture.
Okay.
Probably had it further.
So they don't have a magnetic field probably.
Oh, yeah,
There's a more detailed.
Jupiter has a monster magnetic.
Oh, really?
Yeah.
And it's all gas?
Originally,
Well,
the
they-
sun's coronal magnet.
I don't remember what they say the center is, but it's the gas giant in our solar system.
Okay.
Its surface is gas.
So what does the value of B sub Z represent?
Chuck.
By default, that pop up, I do that.
What orientation of B sub Z increases the likelihood that charged particles from the sun will cause disturbed conditions?
And
And that's all you need to know about B sub Z.
Oh,
You don't have to understand it.
well,
Radio horizon. We normally think of VHF, UHF, repeaters, handy talkies as line of sight devices, vertically polarized typically. And the equation for figuring out the line of sight distance is this 1.21 times the square root of the height in feet. And they, took the diameter of the earth plus that height, and that's where they come up with the 121. And that gives you the distance in miles between your transmitter and where you would make contact with the surface of the earth at that distance, which means somebody same height as you, it could be that far away on the other side of that. Okay.
are they really trying to screw our brains up?
No.
They talk umpteen thousand kilometers to the sun. They
Yeah.
talk feet here, they talk meters of wavelength
No, it's antenna height versus miles.
and miles as opposed to kilometers. Why don't they pick something?
you could use meters here and just use a different scalar instead of
Yeah.
1.21.
Well,
121
It's
to
the
just
ratio.
change that number.
It's the same way
to
when you cut a
7.3.
dipole.
Well, what it would
It's
be.
the same as when you cut a dipole to a quarter wavelength, you can divide the length by meters by a certain thing.
I totally
Or feet.
understand
Or
that,
inches
but
or feet.
The presentation,
Pick one.
the questions are intertwined, metric and.
And you might have to convert them on the fly.
Well,
It's
yeah.
on the lower left, it's square root of 2.
My brain's having trouble.
Okay, well, let's say that you're you're holding your walkie-talkie up and your antenna is 9 feet.
Oh,
Okay.
right.
So 3 times 1.21 is what? 3.6 miles. So you could talk to somebody point to point 7 miles away, right? If they were holding their walkie-talkie up there. However, because it's kind of like the ground wave, you get some curvature. Okay, it can follow the surface of the earth, and they approximate that by changing the formula to the square root of 2 times the height. Okay.
Square 2 times the square root of.
Or the square root of 2 times the height is the same as 1.41 times the square root of the height. Trust me.
You're just saying. 1.4.
So now, okay, we got our 9-foot antenna, and now we're 3 times 1.415. So we've gained another mile or so, right?
It's got me for college.
Yeah.
Right. And it turns out the important part to remember, which I should have done in red, is it increases it by approximately 15%. So you actually get a 15% increase over straight line of sight. And the way they estimate that is they actually used 4/3 of the Earth's diameter in the formula instead of 3/3 of the Earth's diameter. It's just an approximation. I don't know how they actually measure it. Apparently it's close. Except for the fact that we do simplex exercises about once a month. And we've had a guy in Vieira talked to us on Simplex. It's a hell of a lot more than Radio Horizon.
Bureau, not Bureau.
Vieira
Bureau?
in his car
It's strange.
Oh,
because-
so it's here?
in Merritt Island.
Oh, man.
That's a lot more than miles than formula says.
Because in Texas, I had just a regular vertical up about 20 feet. And I could talk to guys in Waco and all over the damn place, and that's 200 miles away.
So maybe it's a little bit of propagation, I don't know. But seems to be more than the Radio Horizon formula says. And in some cases, we have trouble with somebody in Cocoa Beach. So how does the VHF UHF Radio Horizon compare to the geographic horizon, which is the line of sight formula?
Somebody told 15%.
Yeah, who was that? Space weather. Let's see. All this stuff that affects the ionosphere, they tend to call it space weather. So you got solar flares that can increase the amount of radiation up to the point where it can be detrimental. If you're getting just the right amount, I think that's basically what that's saying, to ionize the F1, F2 layers, you can get maximum propagation. If you're getting a whole lot more, that's where you get the effect of increasing the D layer. So you're going to get more absorption of the lower frequencies when you have that. And you also are going to get more background noise. And I was thinking about that. I'm assuming that the sun is going to produce RF noise just like all the other stars that are out there where we get the actual background noise. So I would think that is going to vary depending on sunspot cycles and all those kind of things too.
When the solar activity increases, we get more radiation toward the earth. the
More
F layer-
ionization, right?
Yeah, more ionization, the F layer gets thicker,
Right,
and that's good.
yes,
Bounce off that.
right.
But if it's still high and it gets all the way down to the D level. Yeah, D level, and makes it thicker,
Mhm.
then that's bad.
That's right.
Is
Too
it
much of a
because-
good thing.
Well, wouldn't it bounce off the D layer then? But
Now, for some reason, and I don't understand the physics, the lower frequencies get absorbed in the D layer.
so this must be made up of something differently then.
What's atmosphere?
So this atmosphere.
thin atmosphere.
reflects or refracts.
You know, I mean,
Why wouldn't
we're
this
talking
one?
about what, 40, 50 miles up, so there's not a lot of molecules there.
Yeah, we got more molecules at the lower ones, so
Sure.
more stuff to bounce off of.
Well, but they don't get enough ionization.
But then when they get more ionization.
Yeah, but it apparently doesn't get down below like 40 miles.
Well, right before this, that said, when the ionization, can you go back to slide?
Sure.
Oh, yes.
To which one?
Are you thinking of the troposphere all the way back?
And,
way back?
Take a while.
no, well, don't waste any more time. Yeah, I'm sorry.
Well, what's your question?
If we get more radiation on the F layer, that's good
Mm-hmm.
because it refracts. Okay,
And it changes the amount of refraction. Also, depending on how much it's ionized.
yeah, so if it's ionized really good, then it refracts really good, right?
Yeah,
Okay,
I would assume.
okay, then why doesn't that same logic follow for the D layer?
Maybe because the energy level never gets high enough to affect the high frequency.
Right.
Not enough energy
The hi-
comes down to the D layer to affect the higher frequencies. It only affects the lower frequencies like 7.
The high frequencies go right through the D layer. Exactly why, I don't know.
Because there's not a sufficient energy level.
The higher energy.
True,
levels are
because,
absorbed by
right.
the upper atmosphere.
It happens.
Right.
Remember, as the energy from the sun is passing through the layers of the atmosphere and creating the ions, it's taking energy out of
Right.
the mass from the sun,
Right,
which means that that energy is not available at the higher frequencies to get through to the lower layers to energize something that would be beneficial to the higher frequencies, because that energy got absorbed way up here to increase the ionization of F layer. So that energy band isn't available to energize the lower levels.
Yeah, for every atom or molecule that gets hit from X-rays, UV, whatever, it's basically taking 1 electron volt of energy in order to free that electron to make the ion. It takes that away from the energy coming. So as it goes deeper and deeper, okay, there's less and less energy left.
Tapping off the energy from the incoming.
so we're losing more electrons as we go through.
Creating the ions,
Well, you
Well, that's
just,
creating a positive ion.
but on the incoming energy from the sun, you have less and less available at the lower layers. So it doesn't end up being able to create the ions,
So we
ionization,
become more positive ions
what?
less
the
ionized.
farther down you go.
No, you wouldn't have as much ionization. Because you don't have as much energy left.
You're losing more electrons as you go down.
Well, you're,
Think of it like energy, like energy, not mass. You have to get back to Newtonian stuff here and realize the
Oh,
relationship
okay.
between energy and mass, between a neutral atom having a balanced shell of electrons and a core nucleus.
Okay.
And you beam this thing with energy, and like you said, you kick an energy out of its shell with an electron volt. Now you have an ion because you've got a positively
There's
charged
a positive ion.
atom, but it took
and a negative ion.
and
you have
because
both.
You have the electron freed up.
Electron went somewhere.
You always have,
Yeah.
for every
Pair.
positive, there's a negative in the universe.
And so you've used up the energy to kick that electron out of the shell. So that energy that
No.
affected that atom is not available to continue going down to lower layers.
weaker and weaker and weaker.
So you don't get more energy at lower levels, you don't get more positive, it's just you have more neutral atoms at the lower layer, and when you beam energy at it, then you can create.
So it makes that lower level more dense, so to speak.
Or just use it a lot.
But then,
I think it all starts neutral.
Well, something has to change that lower level with respect to the upper level.
well, you do get some ionization.
And the
Okay,
lower
you don't get as
frequencies
much.
are affected mostly by lower levels of energy.
Yeah.
But then what'll warp your mind a little bit more is remember the top of the atmosphere where the F2 layer is very, very sparse. It's, so there are less molecules and atoms up there to be ionized, even though that's where you get the majority of the radiation. Okay, which is being used up, the energy, as it goes deeper and deeper.
Okay.
Because, and the atmosphere is getting thicker and thicker, so you got more
Filter.
atoms.
Better ratio
Okay.
of.
So I got more atoms down here, but I got less energy to energize them.
Okay.
So the percentage of atoms that get ionized in the lower layers has got to be less. Because there's more atoms than there is up here, and there's less energy to energize them down here. So I'm going to energize maybe all of them in the outer layer, the F2, and then less and less and less.
Okay. I'll work on it.
Okay.
We know you're gonna-
Just make sure you use sunscreen.
Yeah. What's that?
Just make sure you use sunscreen.
Yeah. No.
That's like D-layer stuff. Absorbs the. I guess it absorbs the ultraviolet, right? Doesn't reflect it. Okay, where were we? Oh, increase in background noise too, so.
Yeah.
So what's the cause of short-term radio blackouts? Yep. Which of the following is indicated by a sudden rise in radio background noise across a large portion of the HF spectrum? A CME or an SF? They classify solar flares as either, well, essentially, there's class A and there's class X. There's also a B, C, and M, which, talk about much in between those. The A class are the least intense solar flares. X is the maximum. So an X9 is really, really bad. And the X scale goes up. I guess it's not exactly logarithmic, but it's like a 50% increase between levels. There's this chart showing the relation between those and where the M's are in the middle, and there's also a B that they don't normally show. Basically, the X and the A are the ones that most people care about. So which of the following indicates the greatest solar flare intensity? Okay. NOAA came up with this space weather scale, which they call the G scale. And it goes 1 through 5, where G5 is an extreme geomagnetic storm. And G1 is I think they call it minimal. It's minor. And it's also showing the kind of associated K index levels that go along with those. Because it's all interrelated. It's all part of measuring geomagnetic activity. So which of the following is the space weather term for an extreme geomagnetic storm? Okay. Sunspots. Obviously, the more sunspots, the better propagation. And one of the things they measure is the 304A, which stands for 304 angstroms, which is the wavelength that they're measuring. And it's been so long, I forgot how big an angstrom is, but I do remember it. Um, so they're measuring ultraviolet emissions, and that pretty much is proportional to the amount of F2 ionization. So what does the 304 angstrom solar parameter measure? You didn't think it was 304 gigahertz? Gigahertz? or No, I disagree with him. I disagree with him.
You do?
Yeah. I don't pronounce giant, the giga.
How could you disagree with me?
Does. I forgot his name, but yeah, I got that lecture one day. Okay, so we talked about the ionospheric layers, really three, but F1 and F2 occur in daytime. So actually, I guess you could say there's two at night, four in the day. Average of three. Critical angle is the highest takeoff angle that still refracts back to the Earth. The critical frequency is the highest frequency to refract back to the Earth for a given angle of incidence or takeoff angle. HF scatter is some back scatter and forward scatter that allows you to pick up a signal in the skip zone where you normally not have it. And that's in the E layer where you're getting that scattering. Why that's different, I've never heard of scattering in the F layer, so something unique about E layer, I guess, probably because of the density of the atmosphere at that point, which is going to be different than it is at the F layer.
Just because it's too far away and just
Too far away, they're gonna spread up.
we don't have enough to get through.
You're just not gonna hear any signal that gets through the app because it's scattered somewhere.
Yeah. And we talked about NVIS, or near vertical incident skywave, to do short distance with a high takeoff angle. The propagation prediction, some of the sites that report CW and digital modes from the beacons and things. PSK reporter shows all the FT8 and FT4 stuff. You ever look at that? No, you should. Yeah. You can see who's hearing you. It's a neat map. Huh?
Your screen, VOA now. Voice over there.
Yeah, there's an A left off. But vocap's easier to say than voicap.
Yeah, yes.
The A index is the long-term or once a day measure average over the day, and the K is the every 3 hour one. And the B sub Z is the one nobody understands, which is showing the direction of the geomagnetic effect, whether it's north or south. South is bad, but I suspect north is not good either.
What I read was it says that southward is towards the earth.
Huh?
It says that southward is towards the earth. So the radiation coming towards the earth is going to affect this one.
Well, how could be south? How would south mean towards the earth?
It's from the sun, I guess the southern.
If the sun is north and the earth's surface is south. Ignore the magnetic.
Let's not talk about that.
Next, this is one of those memorized, don't understand.
I thought the sun was sort of east or west, depending on the time of day.
It is always north, it's up, right?
Yeah, but on the equator, if I look up, I see it, which means it's in the plane of the equator, right?
Point where they clear up that equinox.
Yeah. The radiation, the radio horizon is approximately 15% farther away than the line of sight or the equatorial horizon. And solar flares probably have the major effect on HF propagation. As far as daily activity. And we measure those class A and class X categories. And MEs can cause a sudden rise of background noise when it's going to miss us. If it's headed for us, we are in doo-doo. The G scale done by NOAA is showing minor to extreme levels of geomagnetic conditions. I guess they don't show as G0, but I guess if you're not having any, I would assume you don't have a G1 through G5 rating. And the 304 angstrom measurement is measuring ultraviolet emissions. And it's kind of an indicator of how well the F2 layer is being ionized, since it's mostly ultraviolet that's doing it. The major, besides infrared, I think the major radiation out of the sun is ultraviolet.
Again, what is the scale for through the 304?
Angstrom?
Is it 1 to 9 or what is it?
For which metric you're asking about?
The 304 A? Is that
Yeah.
what it is?
I don't know.
Oh,
I didn't look it up. It wasn't a question. It was
so-
hard enough to research all the stuff there's questions for.
so what are we
Angstrom's approximately the size.
It's
of
just,
an atom.
it's just a measure of ultraviolet radiation, basically,
So.
which is an indicator of how well the F layer is being ionized.
It's a number of something.
It's a number,
Say 304 A
Right.
is
and I assume a bigger number means more.
Maybe a question is, what's the unit of measurement?
Yeah.
Something like a watts per square
well,
meter.
no, not so much the
Radiation.
unit. What's the scale?
Yeah, well, the point is, if you know what the unit is of measurement, then you can at that point figure out what the scale is.
Okay,
Like if
so
it's watts per square meter in complete darkness, you have 0 watts of energy. I'm just making that up from what the solar industry does.
or do we look on a chart and we see a column for 304 E, 304 A?
If you remember that one chart I showed early on with the picture of the sun and all that stuff, 304A was one of those parameters.
Yeah, I think what I was asking is, what were the column of numbers?
No, it was just showing the solar flux index and the solar flare number and the A index and the K index and the G, and all of those things were all in that one site.
Okay,
And that's something, I think that was the ARL one, which I get for some reason frequently because I checked something at one time.
Check the box.
Yeah, Dan's got it
Yeah,
there.
that's on the QRZ page, but they might get that from.
I think it came from ARL.
yeah,
And it's got, let's see, third or fourth line down there is 304A. And it shows, looks like it. Huh. Says 142.7 at SEM. I'd have to look it up.
At SEM,
1.7.
142.7.
Oh, 142.
yeah. So now you know what the number is, but what's
Yeah.
that mean?
That means
So
squat.
everybody needs to go home and turn your radio on because it says good propagation for pretty much everything today.
All right.
It was good this morning when I, before I
Yeah.
Perfect time for me not to have an antenna.
talking to Australia on 20 meters.